Okay, this question asks us to consider the problem of minimization, a minimization problem of f, and the constraints are x1, x2 both greater than or equal to 0. And suppose that gradient of f at 0 is non-zero, it's not a zero vector, and the partial derivatives of f, both of the partial derivatives of f at 0 are non-positive, or less than or equal to 0. And the question is, how do we show that 0 is not, it cannot be a minimizer of this problem? Okay, so to show that, we just need to see if 0, if the first order necessary condition or the second order necessary condition is violated at the point 0. Okay, if they are violated, then the 0 cannot be local minimizer. All right. So the problem is given like this, and this is the constraint set. So the x can only be here, including the two x's. And to check the first order necessary condition, we need to show that for any feasible direction d, the directional derivative of f along the direction d must be greater than or equal to 0. Okay, so we need to show that if we want to show that at point 0 the second order necessary condition is violated, we just need to show that there exists some feasible direction d such that the directional derivative of f at 0 along the direction d is not non-negative, meaning that it could be negative. Okay, so that's how we show that this is the first order necessary condition is violated for some feasible direction d. So the d could be anything like this or this or this or this, right? Any of those directions. So we need to check if any of these directions will make this happen. Okay, so the gradient of f, we don't know the actual form of f, but the only information we know is that the gradient of f is this, and both of the components are less than or equal to 0. And it is non-zero, meaning that at least one of this is strictly negative. Okay, that's what we know. The other thing is that the d is something like this. So we know that it's a feasible direction as long as both of these d1, d2 are non-negative, right? So imagine this case, if since this partial of f, partial f dx1, partial f dx2, they are both less than or equal to 0. That means I can choose my d to be negative of this. So if I d1 is just a negative of partial f, partial x1 at 0, d2 is a negative partial f, partial x2 at 0, then I know that both of these are greater than or equal to 0, right? Because these are negative. Then it's both less than or equal to 0. The negative of them will be greater than or equal to 0. That means d will be a feasible direction, right? So it's a feasible direction, and then let's check the inner product of the gradient of f at 0 with d. So I just choose my d to be negative gradient of f at 0. Then the gradient of f of at 0 times d, just plug in this here into this d, then we'll get a negative of gradient f squared, right? Because it's just the inner product of gradient f at 0 with itself, with the negative sign in front. But the gradient f is non-zero vector, so it's that in the question. So this means that this norm must be strictly positive, right? Its norm is 0 if and only if the inside is 0. So it's non-zero, then this whole thing will be positive. And then you have a negative sign in the front, that becomes a negative. And this will violate the first order necessary condition. So by choosing d to be negative the gradient of f at 0, we'll show that the directional derivative of f along direction d will be a negative value, and that means 0 cannot be a minimizer since the first order necessary condition is violated.